When I heard about chaos theory, I really wanted to study it so that I could understand what it was and how you might potentially use it. And at that point in time, there was quite a buzz around chaos theory. I still remember in the first Jurassic Park movie how cool the character of Dr. Ian Malcolm was, and how amazing it must be to understand this theory of chaos and to be able to apply it to real things. But probably what I remember even more than that was reading the novel and seeing these funny little sketches mapping out a pattern with squares in it. And that was probably the first time I came across the concept of self-similarity and fractals. I didn't know what these things were, but I knew if I got the chance, I would make the effort to find out. To explain again what fractals are, a fractal shape is composed of smaller copies of itself, which in turn are composed of even smaller copies, and so on. This is the point that the patterns in the Jurassic Park novel were making, and this sort of characteristic is called self-similarity. Fractals can be found in natural phenomena such as snowflakes, coastlines, but also in data of complex systems such as turbulence, earthquakes, and financial markets. What I learned later though, and I didn't know at the time, was that chaos and fractals are not the same thing. There are connections, but they are not the same thing. To see how well understood this difference is, I did a quick survey of videos on YouTube which talk about chaos theory and fractals and their application to financial markets. And here's what I found. Most of the videos are reasonably accurate in their description of chaos theory, but the description of chaos theory is fairly hand-wavy and not a lot of detail is given. Some point out that chaos is not the same thing as randomness, and that chaos can bring about order, which are great points to make. But all the videos I saw merely conflated the concepts of fractals and chaos together. One, for example, describes self-similarity as being a key property of chaos, which is kind of the same thing as calling something a fractal. And based on what we saw in the Jurassic Park novel, you might think, hey, that's true. But the simple reality is no, chaos doesn't necessarily imply self-similarity. And when I explain what I found was the difference, hopefully you will have the same epiphany as I did. But to summarize the situation, most discussions on chaos and fractals that you'll find targeted at non-mathematicians make this oversimplification, which is a shame because even if you aren't into math, you can still draw useful insights by understanding this difference. So what did I find was the difference when I looked into this while I was doing my PhD in physics? Well, you can think of it like this. Chaos describes the unpredictability of markets, whereas fractals characterize the spikiness of markets and how markets can go through periods of relatively small movements and then seemingly suddenly start to exhibit very big spikes up and down. And this is related to the self-similarity that we see in financial markets. So fractals are much more about characterizing the nature of this spikiness and the cluster volatility that goes along with that. And both of those things are related to a parameter called the fractal dimension. In fact, the kind of fractal pattern you see in financial market data is only partly due to dynamics, which are strictly related to chaos. You also have to think about things like complexity theory and emergent behavior. And these are the properties which actually cause the self-similarity. And those types of dynamics are sometimes referred to as high-dimensional chaos. But those are subjects we will leave for later videos. So chaos is only one part of what is going on in financial market dynamics. But here's the key difference between chaos and fractals. Chaos was discovered as a property of equations that can be written down and used to make predictions. These equations have a small number of variables, so they are often called low-dimensional chaos for this reason. It's this ability to describe the evolution of chaotic systems with equations that makes chaos different from fractals. And it's not that the future can't be predicted from these equations, it's that the long-term outcomes of such systems are incredibly dependent on the initial conditions. And this is the origin of the often quoted butterfly effect that, supposedly, a butterfly flapping its wings on one side of the world will make an enormous difference to the weather on the other side. So here we will look at how the variables in a set of chaotic equations called the Lorentz equations change over time. We'll start with two sets of initial conditions, represented by a blue dot and by a red dot, which start out very close together. As we calculate the new position of each of the dots from the Lorentz equations, we see that the paths initially are fairly similar, but eventually the path each dot follows begins to diverge from the other dot. Until ultimately they end up following quite different paths. So you might say, so what? We can still describe the future. But in reality, it's pretty much impossible to estimate the starting position of a real-world system accurately enough that the mathematical model will predict its future position at some distant point in time. That is to say, any error in estimating the initial positions will grow exponentially over time. Now with fractals, by contrast, and as far as I know this is still the case, no one has come up with a set of physics equations of a similar nature to these, which actually produce the fractal and self-similar behavior we see in financial market data and in other similar complex systems. And that's even though we have equations to describe phenomena like turbulence, and those equations are called the Navier-Stokes equations. Though they describe many aspects of turbulence, the self-similar fractal properties of turbulence, which are extremely similar to those of financial markets, do not fall out of these equations. And for financial markets, there aren't any similar equations to the Navier-Stokes. The system of financial markets is far more complicated because it depends on all kinds of things, not least of all, human behavior, which is really difficult to model mathematically. So fractals are not a dynamic model in the same way that chaotic equations are. So there's no way you can write down an equation that is going to describe the progress of the system into the future. Rather, they are more of a statistical method for characterizing how markets behave, and for understanding that you can suddenly get quite big movements and that these movements tend to be clustered together in time. And people who use quantitative finance with subjects like econophysics understand or need to be able to understand fractals and fractal properties and use these properties when they do things like calculate the fair price of derivative contracts like options. So to talk about the chaos theory of markets and imply that this is all wrapped up with self-similarity, or to use the terms fractals and chaos interchangeably, is at best highly simplified and at worst simply wrong. And I feel that you will personally benefit by understanding that there is a difference between these two things. So I hope you enjoyed this video and learned something from it. Tell me in the comments below whether you understood this difference before watching this video, and whether there are other related subjects discussed on YouTube that you would like to see a critical review of on this channel. Thanks for watching.